All right, welcome to this installment in the video series about this house here at 3612 Ida Bell Lane. This one's all about airtightness, what makes it great, and why we don't need to be afraid of it. I wanted to make this video because this whole idea of airtight construction has been the source of a lot of controversy in the construction industry, particularly in the residential sector of the construction industry for a long time. But I'm here to tell you that, there's really nothing to be afraid of here. Ultimately, it all comes back to what I alluded to in the introductory video, if you happened to catch that one, which is that you've just got to make sure that the building is considered as a whole system and that each part of that system is designed with the other parts in mind. That's how you get harmony and integrated systems that perform really well. So, we've often heard it said that you need for a building to breathe, that you can get a house too tight. And I would argue that where these statements are coming from, and I think you can hear an element of concern or fear kind of in the backdrop of those statements. And I'd argue that where these things are coming from are experiences that people have had in buildings where they may have been built airtight without considering what that airtightness means for the rest of the systems in the building. Ultimately, it just comes down to making sure that the building manages water well and that the building is well ventilated. That's all we need to do when it comes to airtight construction in order to have a safe and healthy outcome. We've done that here. You can find out how in the other videos in this series. But let's get into the details of all that and talk about the ways that airtightness really benefits a building, how it can really increase the indoor air quality and comfort of a building, and also the ways that we need to be sure to incorporate other systems in the building to make that work really well. Okay, so why we like airtight construction. Ultimately, it comes down to this idea of control. If we want to provide the best possible comfort experience and the highest possible indoor air quality, we need to get as much control over that indoor air mass as we can. And by providing a really airtight separation around that indoor air mass to keep the outside air from getting into it, from keeping it from leaking away, that's how we establish that baseline of control over the air in the building so that we can then condition it really well and ventilate it in ways that make sense so that our air quality or our comfort are as high as they can possibly be. When you run into problems with airtightness, it usually has to do with a lack of one of two things. Either the water management strategy of the building was insufficient, or the ventilation strategy for the building was insufficient, or in some cases both. Air sealing makes a building less able to dry, and as you can guess, it makes everything within that indoor air mass very well contained. So, from the standpoint of water management, we just have to recognize that when we make an airtight building, we've removed one of the elements that dries water out, which is the movement of air. That's why we put fans on spills in remediation work. That's why, the hairdryer blows the air and doesn't just, heat it up by contact. That's why the, the fan in the bathroom is blowing air and not just like giving you a warm surface to touch. The movement of air is part of how water dries out faster. And so by air sealing a building, we do remove that element. Well, all that means is we've got to account for that in the way that we put together the water management layer of that building so that it can manage water without needing to have air moving across the building enclosure. And you can learn more about how we did that on this house in the water management video. Really, it comes down to a few basic things. Flashing, ventilation behind the siding. Those are two of the biggest things that if you can just get those two things right, you're well on your way to having a really good water management strategy that makes an air barrier safe to have behind that wall assembly. Now, the other dynamic that I mentioned, as far as an airtight building making everything really contained, has to do with water vapor, okay? That's humidity in the air. Airtight buildings can often become too humid if the ventilation strategy isn't right. So that'll cause problems it'll cause problems any time of the year really, but you'll have, if you don't have a good insulation layer in the wintertime and you've got too much humidity indoors, you'll get condensation on indoor surfaces that with the right conditions can lead to mold growth. Obviously that's a huge problem. It goes the same way in the summertime, where here in our hot, humid climate, you can really get some humidity building up inside when that environment is so well contained, and that's just why it's so important to ventilate. And that's what we mean when we say a building needs to breathe, right? We need it to be ventilated, because otherwise it just gets stagnant. It gets, stale and musty, and obviously that's a problem, and that's why you just have to have a plan that accounts for that and can manage that dynamic within the context of an airtight building enclosure. So what we have here is a fresh air ventilation system that's going to provide active air exchange on controlled terms. That's going to provide a really high level of indoor air quality here, because we're bringing our outdoor in under some very controlled parameters. We have a device in the crawl space that has some dials that control when it operates and how much air it moves. It's got a core inside that preconditions the air as it's coming in, which exchanges some of that humidity and kicks it back out so that we're not bringing a ton of humidity into this house. It's got a really great filter to remove airborne particulates and make sure that the air that we're supplying to this building is actually way healthier than the air that would be coming in by accidental means if we intentionally left the building leaky and relied on that air leakage for our ventilation. And I think that's one of the biggest things to realize about the concern over getting a house too tight, is that if let's say that you hold this belief, you don't want to build too tight, what you're really saying is, I want my building to leak, right? I don't want to get it so sealed up. And the reason is because I'm concerned about air stagnation. I might be concerned about humidity buildup and mold growth and things like that. Very, very valid concerns, but leaving leakage in the building is really not the best way to address those concerns. Because think about it. If we're relying on if we're relying on air leakage for our ventilation, we don't know when that air is coming in and when it's not. We don't really know where it's coming from or what pathway it's taking to get inside. We don't know really how much is coming in, and so we don't really know if it's enough or if it's too much or whatever. And so air leakage is really not a good mechanism for that. It's accidental, it's uncontrolled, it's unintentional, and it really is not the way that we want to ventilate our buildings. You think about the way air moves throughout a building in, under natural conditions. That's driven by a couple of different things. One thing is the stack effect. That has to do with an indoor-outdoor temperature difference, which is what creates the pressure to move the air in and out of the building. Basically, it's like this. When you have a warm air mass, like the heated indoors in the wintertime, surrounded by a cold air mass, that warm air is less dense and it wants to float upward. And this is what we are talking about when we say that heat rises. What we're really saying is that warm air moves above cold air because of a density difference. If we're in a leaky building, as that warm air moves upward, it's going to find opportunities to escape through high points in the building. And as it does so, the building's placed under a suction pressure that requires it to suck air to make up for that in an equal amount simultaneously from low points in the building. Now, you may have lived in a house with a gross crawl space. If this dynamic is happening in your building, a lot of the air that's entering the building is coming through that gross crawl space. That's an air quality problem. The crawl space dynamics that I see most of here are not favorable. I mean, you would not want to go down there and breathe the air all the time, but in fact, we're letting it into our homes via air leakage a lot more than we'd like to think. And so that's one dynamic that we want to avoid, right? Because if that's our ventilation strategy, we're really not doing ourselves any favors. The other thing that triggers is an energy penalty, because we've got air that we've paid to heat leaving and escaping. So there goes that money that we've put into that air for the heating value of it. Meanwhile, we're drawing that cold, unconditioned air into the house, where it then has to be dealt with by the heat and air system. So now that heat and air system has to work harder to condition the air because it's starting from a less desirable starting point with how cold that air is. Whereas in a more airtight building, it can recirculate and recondition the air that's already conditioned in that building, meaning that its load is way lower, energy efficiency is greatly enhanced. The opposite effect happens in the summertime here in our part of the country, where when you have a cold air mass surrounded by a hot air mass, just like we do when we're air conditioning on a really hot summer day like today, that cold air is denser. It wants to sink below the hot air. And so we'll have air leaking out of the house through low points. And as it does, just like in the other example, the house has to suck in air from elsewhere to make up for that. And that's going to be coming from places up high, such as an attic or, other places like that. And with that hot air coming in, it's going to bring with it not just the heat, it's going to bring a lot of humidity with it as well. And especially if it's traveling through an unconditioned attic space that may be dark and dusty, a lot of pollutants and allergens can come with that air as it travels through the attic and into the house because of air leakage. So is that a good ventilation strategy? Is that a good drying mechanism for our homes? And I would say a heartfelt no, because if we're talking about ventilation, obviously we've got an air quality problem with all of the dust that comes from that attic. But if we're talking about drying ability for the house, if we're using air leakage as our ventilation strategy, letting a ton of humidity into the house is really not productive from a drying standpoint. In fact, I've actually seen this go the other way and add moisture to a house and result in elevated indoor humidity levels that in some cases can rise high enough for the surfaces and contents in the home to start growing mold. You may have seen little beads of condensation of liquid water droplets forming along the bottoms of the sheet metal vent openings for the heat and air system in the ceiling of a poorly insulated house. That's a result of all the humidity in that attic air finding that cold sheet metal surface and creating condensation as it passes by it because of the air leak that exists around the drywall cutout for that heat and air vent to poke through. If left unchecked, that can create mold inside your building, and that's an air quality problem, and it's a durability problem too, in addition to the whole energy thing. So all that to say, air leakage is not as helpful as we want it to be when it comes to the way our buildings dry and the way our buildings breathe. Wouldn't you much rather have more control than that over the air that's inside the house? And I would argue, yes, that is a good thing. And again, the way you establish that control is a more robust air separation around that indoor air mass so that you eliminate all those unknowns about what air is coming in and from where and when and how much and all that stuff. What else is in that air that may be coming in, as well as losing the air that you've paid to filter and condition. I think we can do better. And on this house, that's what we've tried to do. We got a really good air tightness score here. There's a way of measuring that, and I won't get into the details of all that, but what you need to understand is that the building code has requirements about this stuff. The building code recognizes air tightness as an important thing to achieve in new construction, and the level of air tightness that's currently in force for our part of the country right here in our jurisdiction where we built this house is 7 air changes per hour when measured at the standard test pressure that we put the building under when we're testing for this stuff. In other words, what that means is that the air in the building, like the entire volume of indoor air mass, will be completely evacuated and replaced 7 times over the course of 1 hour at that test pressure. So 7 air changes is what the building code wants us to get, or less. We can be tighter than that, but we can't be any looser, all right? We are at 1.4 here, and I'm really excited about that because with a little bit of fuzzy math, that's roughly 5 times better than what the current legal requirement is. Now, we happen to be on a version of the building code here that is a little out of date. Now, the energy code that governs the air tightness requirement in our area is, in theory, the 2018 version. So the building codes are updated every 3 years. They're on a cycle like that, and every 3 years a new version comes out with some minor modifications and updates and things. So we're currently on the 2018 version of the Energy Code, except that at the state level, the state of Tennessee decided that they would amend in the requirements from the 2009 version of the Energy Code book. So in theory, we're on the 2018, but we're really on the 2009, and that's where that 7-air change requirement comes from. Now, the more recent versions of the code, beginning in 2012 and onward, changed that air tightness requirement here in our climate zone from 7 down to 3, okay? So other parts of the country are on that code. Other parts of the country are building much tighter than we are here even now. But at this house here on Ida Bell Lane, we're still more than twice as good as what the most recent requirement of the building code would want you to build to. And so I think that's really great. And what that's going to translate into for you as the potential owner of this place is that you're going to have that control over the indoor environment, and you're bringing in your fresh air in a controlled way. You know where it's coming from. You know all there is to know about it, how much of it is coming in because it's setting. There's a setting on the machine, when it's coming in because there's a setting on the machine. You can inspect that filter to see how dirty it's getting. You can inspect that core to ensure that it's still operating as intended. And so that's how we want our buildings to breathe. So I don't dispute that buildings need to breathe at all. I just think that there's a really great way of getting them to breathe and ways that are just really not so great of getting them to breathe. And we wanted to do it the good way here. So that's what we've tried to do. And then as far as the whole humidity management thing goes, number one, a good air seal keeps a lot of humidity out in the first place. And then a right-sized air conditioning system manages that humidity by having run times that are appropriate to the space that it's serving. The way that an air conditioner manages humidity is that as it cools the air, it's also dehumidifying the air at the same time, because there's this really cold coil that all the air passes through as it moves through that air conditioning, and that's where that heat is dumped and that cold is given to it. But it creates a lot of condensation because that surface of that coil is so cold. And all the water that condensates out of the air is essentially dehumidification. We're extracting water and moisture out of that air, turning it into liquid water, and that gets drained to the outside. So the air conditioner is actually a really powerful dehumidifier, and that's great, but it doesn't work if it's not running, okay? We need that air conditioner to cycle a certain amount of the time, not just for temperature control, but for humidity control as well. And so in a really well-designed airtight building, such as the one that you're looking at right now, that air barrier is going to do the really heavy lifting of keeping that humidity out in the first place. And if you have a right-sized mechanical system, that air conditioning is going to be running often enough and cycling that air long enough that it's extracting what humidity remains and dealing with it so that it never gets out of hand. And that's how we prevent things like condensation and mold growth on the interior this time of year. So that's our air quality win, that's our comfort win, that's our energy efficiency win, and it's just good peace of mind that you're living in a place that operates like it should. All right, I've got one other dynamic that's important to talk about concerning uncontrolled air leakage in and out of a building. And it overlaps with this concept of getting your mechanical system to the inside of your conditioned space. And that's when your mechanical system is not inside conditioned space. Most often, this results in actually accelerating and exacerbating the dynamics by which uncontrolled air movement can infiltrate your living space. And so what happens is like this. If you imagine that you have your heat and air system put up into a hot attic or a vented crawl space where it's outside of the conditioned zone that it's serving, you have a lot of opportunity for duct leakage. And most of that opportunity exists on the supply side of that system, meaning that there's usually more leaking out of the ducts going to the house than there is leaking into the duct coming from the house, right? That return side is usually much simpler and therefore has less opportunity to leak. When you have this unbalanced leakage, the house is under suction. And the reason is that the blower fan in that heat and air system is sucking more air back up out of the house than it's giving back to the house through the supply side, which leaves the house under a net suction effect that must be relieved. And the house has to relieve that suction by bringing air in from other places to make up for that deficit that it's not getting back compared to what's being taken from it. So those leaks are going to be the pathways where that air travels to relieve the suction created by the heat and air system. And if you have a lot of leaks open to your attic, that means you're going to be sucking, like actively sucking attic air down into the house. If you have leaks in your crawl space, you will be actively pulling crawl space air into the house or from the outdoors or what have you. So that's a really important thing. And so, you know, in the absence of a good air barrier and in the absence of a really well-sealed duct system, you actually make small problems into big problems that way. I alluded to an experience earlier in the video where, you know, this comes from a home I'm actively working on right now, where the owner noticed a fuzzy mold growth beginning on many of the surfaces and contents indoors over the course of one summer in a 3-year-old home. And this is precisely the dynamic that's at play here. There's a lot of leakage between the house and the attic. There's also a lot of leakage between the attached garage and the living space. And there's a heat and air system that is not only very leaky when it concerns the ducts, but it's also oversized. It's too powerful for the zone that it's being asked to serve. And so what's going on there is that whenever it's cycling, it's putting the house under that suction pressure that I described a minute ago. And the relief for that suction is coming from the attic, and it's coming from the garage, and it's coming from outdoors. And this time of year, there's so much humidity in the air that we are just dumping a tremendous amount of humidity into that home by accelerating that air leakage. And so in order to lighten the load, so to speak, that house has to get more airtight. We've got to keep the humidity from being able to come in. That duct system has to become more airtight because it's not inside of the conditioned envelope, and therefore that leakage really matters because it's the mechanism by which we're accelerating that hot, humid air entry into the living space. But it gets worse because the heat and air system being oversized means that it's satisfying the thermostat really fast because of all the horsepower that it has to cool that house. And so the temperature is being satisfied very quickly, which means that the cycle times aren't quite long enough for the air in the home to spend enough time passing over that cold coil to fully extract all that humidity that we're sucking in to the indoor air mass from the attic and the garage. So we have these shorter cycle times, which results in inadequate dehumidification. But when the thing is running, it's adding humidity to the space faster than it's taking it out. And that's where that net humidity buildup is coming from. And that's what's leading to the mold issue that she experienced. Now, even in the absence of liquid water, mold growth is possible on a surface when the relative humidity at that surface is 70% or more. You know, the more, the worse, right? And so, yeah, she's been reading elevated indoor humidity over the course of a couple of summers, trying all kinds of things, damp rid bags, dehumidifiers, and so forth, and nothing seems to be able to get it under control. We are hopefully very soon mobilizing to get out there and get that place better air sealed. And we'll be having an integrated dehumidifier installed into that heat and air system to ensure that humidity is positively controlled in that building. But these are the things that you run into with a building that breathes, and particularly with an air system that's not inside the conditioned space, and that in this case is too large for the zone that it's serving. So all really important reasons why it's so good to think of the building as a system, to make sure that the mechanicals are appropriately sized and that the design and selection of those mechanicals recognize the other components of the system that it's being asked to serve, why the building enclosure is so important to get tight, and you know, some of the pitfalls that happen when you don't and some of the benefits that happen when you do. So hopefully that sums it all up for you. I want to thank you for checking out this video. And if you want more information on how we got this house airtight and the other things that we did in this house, including a fresh air ventilation system and a conditioned crawl space and the water management details that we performed here, check around the other videos in this series. We thank you for your time spent. Hopefully you learned something, and thanks for watching.